Now let's see this. Given a relation ABCD and FDs are given like this, decompose R into Bcnf. So before decomposing it, let's see whether this table is in Bcnf or not. Now we have to find out what are the candidate keys on this table. Now if you see this, C and D are on the right hand side, so I'm marking them, and D is there on the right hand side. Only attribute which is not there on the right hand side is B. Therefore every candidate key is supposed to contain B. Now let me test if B itself is enough to become the candidate key, right? So for that I am finding out B plus. If I find out B plus, I'll get only B from this, check it. I'll not get anything. So what does it mean? B should be a part of candidate key, every candidate key should contain it, but only B is not sufficient to become the candidate key. Therefore we are supposed to add some more to B. Now let's try adding one attribute. So what are the various combinations we get if I add only one attribute? See, why am I adding only one attribute? Before adding two attributes, let me test if one attribute is enough. Then that will become the candidate key. I need not add two attributes, right? So let's go that way. Now this is the essential part. Now to this essential part I am adding one more attribute. So what is it? What are the combinations I get? To B I can either add A, or I can either add C, or I can either add D. Right? Now if you see this, out of these three keys or out of these three possibilities, always B is present. That is what is important. Every key should contain B. That is why I get only these three. Why am I not writing A, C and C, D? Because they don't contain B. Even though they are containing only two attributes, I cannot write CD because it can never be a candidate key because B is not present, or I cannot write AD because it can never be a candidate key because B is not present, right? Every candidate key should definitely contain B because it can never be determined without including B in the candidate keys. Got it? So I need to check only these three. I hope you understood why I discarded the remaining possibilities which are containing two attributes, right? Okay, and now what is it? You get AB here. Because of AB and because of this FD, I am going to get CD. So I got ABCD, right? Now what does it mean? AB is the candidate key. So one of the candidate keys for this table is AB. I cannot say that AB is the only candidate key in this case because there is a possibility that any of these are also going to be candidate keys. Okay, now what about CB? If you find out CB plus, I get CB and nothing else. So CB cannot be the candidate key. What about DB? I get DB, and because of D I get A, right? And now I got AB, and because of AB I get C, isn't it? Therefore this can also be the candidate key. So what are the candidate keys now? A, B and D, B. So these are the only two candidate keys which are going to contain two attributes. Now if you try to find out the candidate keys which are containing three attributes, which should not contain, which should not be a superset of these two, right? What I mean by this is, you cannot say that ABC or ABD is a candidate key. The reason is already AB and AB is candidate key, therefore they are going to be super keys. They cannot be candidate keys. Got it? And so we need not check them, right? And what about this one? You cannot say ADB or CDB is a candidate key. You need not check them, or even if they qualify, you cannot call them the candidate keys because they are going to be super keys, right? Now what is the only other candidate key with three possibilities, with three attributes, which are not these four, right? So only other might be A, D, C, isn't it? And this cannot be a candidate key because if you try to find out the closure, you are not going to get B there. You can try it, you are not going to get B. Why? If you see the closure, it is going to be ADC, that's it, and D is again going to give us A, right? And nothing else. So you are not going to get B. So there will be no candidate key with three attributes or four attributes. If you take four attributes, that is obviously going to contain these two attributes. Got it? Therefore these are the only two candidate keys possible. Okay, now we have to check whether the table is in Bcnf or not. Before going for that, let's just see, even though it is not required, whether the table is in third normal form or not. How can you check it? By the formalized definition, you can check whether the left side is a super key or not, and the right side is a prime attribute or not. Now if you see this functional dependency holds on this. Now the left side is a super key. Why? AB is a candidate key. And if you see this one, the right side is a prime attribute, isn't it? Therefore, according to the formalized definition, this table is in third normal form, right? Because the first one is satisfying the condition A, and this one is satisfying the condition B. Got it? So either A or B, if it satisfies, then it is enough. Got it? Okay, now let's try to find out whether this table is in Bcnf or not. So how to find it out? See this. So the left side is a super key. So what is the definition of Bcnf? If any functional dependency holds on the table, then the left side should always be a super key. Yes, this one holds on this, and left side is a super key. Fine. Then what about this one? This one holds on that, but the left side is not the super key, isn't it? Therefore, what is that you are supposed to do? Decompose it by finding out the closure of the left side of the FD, which is not satisfying. So A, B, C, D. Find out the closure of left side, which means D plus, then I get DA. What does it mean? D is going to take away with it the attribute A. Now what is remaining? B, C, D. Let D be staying there. Why? Because we need a common attribute which is going to be a candidate key for one of them. In this table, D is the candidate key, and the remaining table is B, C, D. Now what are the attributes what are the functional dependencies applicable on each one? Now the functional dependency that holds on this table is D determines A, and the functional dependency which holds on this table is, if you see it, this cannot hold on this because A is not present, and this cannot hold on this because A is not present. Therefore, no functional dependency will hold on this table, right? And when no functional dependencies hold on a table, then what can we say? It is in the highest normal form possible. The reason is, a table will not be in some normal form if the functional dependency is failing some condition. But if there is no functional dependency to check any condition, then definitely the table is in highest normal form. Got it? And since there are no functional dependencies, you have to take the entire table as candidate key. So for this table, BCD is the candidate key and no functional dependency applicable on this. And for this table, D is the candidate key and only functional dependency which is holding on this one is it, and the left side is the super key. Therefore, we can say that this is in Bcnf and this is in Bcnf. So the tables are in Bcnf. And also the decomposition is lossless because the common attribute D is a candidate key for one of the tables, right? Now what about the functional dependency preserving? Now finally we got only one functional dependency, which is D determines A. Out of these two, I got only one, right? Now let me see whether this set is containing in fact only one. This set of FDs is covering this set of FDs or not. In that case, we can say that the functional dependencies are also preserved. How to check it? Clearly, this set is covering this functional dependency because it is already present there. Now what about this one? To check it, we have to find out AB plus using this set and see whether we are getting CD in that or not. Now if I find out AB plus, I get AB, and I have to find out AB plus only using this function FD set. Now from this FD set I will not get anything else, which means I will not get CD, which means this particular functional dependency is lost forever. So what happened here? We are able to decompose the table into Bcnf by creating these two tables, and we are able to get lossless decomposition, but FDs are not preserved here. One of the FD is lost. In fact, this FD is lost. Got it? Okay.